great spatial work on thaw slumps, changes in vegetation, and a lot of other things. So that's what inspired me. Thaw slumps in particular is what inspired me to invite Dave to do this talk. So please welcome Dave Swanson.
All right, thanks, Ken. So, right, we can. Right, I work for the National Park Service and the Inventory Monitoring Program, and we monitor a variety of natural resources in the parks, which we call vital signs, and I'm responsible for several of them. One of which is the permafrost vital sign, and as a part of the permafrost vital sign, we're monitoring ground temperatures and certain permafrost thaw landforms, and which one is retrogressive thaw slumps. They're a dramatic thaw landform that is one of the projects that forms a part of the vital sign monitoring for the permafrost vital sign. So I'm going to talk about that today, and the all of the work that I'll be presenting today is supported by the National Park Service as a part of the Inventory and Monitoring Program. So my field area is the 5 National Park Service units that are in north central, northwestern Alaska, known collectively as the Arctic and Inventory and Monitoring Network. They've been aggregated for the purposes of monitoring. And they cover about 82,000 square kilometers, which is actually about a quarter of the area of all national parks in the United States, big parks. So that's my responsibility then is to monitor permafrost in these national parks. And this area, many of you are of course familiar with it. It's an area of mostly continuous permafrost, and in fact, all of the thaw slumps that I'll be showing you are actually in the continuous permafrost zone. So that's the study area. And so what is a retrogressive thaw slump? These are dramatic permafrost thaw features. They exhibit both thermokarst and thermal erosion, so there's both subsidence and basically thaw-assisted erosion going on. And this is kind of a typical one here, not a big fancy one, but more of there's a lot of these kind of middle of the road slumps like is displayed in this slide here. They're tens to hundreds of meters wide and long. They tend to be kind of oblong shaped. They're not really long and narrow like the active layer detachments that they resemble in some ways. And they have an escarpment at the upper end that can be anywhere from 1 meter to more than 20 meters high. They are found on slopes, frequently near rivers or lakes, and for that reason, they're of concern because you frequently see a plume of sediment running down the river, or the lake that they're next to can be turbid as a result of the erosion from the thaw slump. So that's kind of what attracted our attention to them to make them one of our monitoring objects of monitoring, because they do have these kind of impacts on water quality. And one other thing about retrogressive thaw slumps is they're long-lived. They can grow for a decade or more by that escarpment advancing uphill. So here's just another view of a thaw slump, so you can get a feel for the mechanism of their growth. So there's this escarpment at the top, and this is where the most active thaw is going. You've got ice-rich permafrost. That's one of the requirements, is it's got to be ice-rich stuff. Thawing, and then since it's got more water in it than sediment, it turns into this mud water slurry that oozes downslope, and then as it oozes downslope, it basically dewaters and eventually grinds to a halt, and then further erosion below there happens by conventional water erosion. So you've got the water coming because of the permafrost thaw from the ground ice, and also any runoff that's coming from rain or the landscape surrounding the thaw can end up eroding that stuff out and further on into whatever water bodies might be nearby, if there are any. I've labeled this main scarp. If you get into the thaw slump literature at all, you'll see that almost everybody calls them headwalls, and I'm being a little contrary here. There's a long literature of landslides that's been around for many decades where all of these are always called main scarps or occasionally head scarps, and so I actually prefer that term. it seems that permafrost scientists adopted the term that is applied to actually to the cliffs that sit at the top of glaciers for their features. But I sort of prefer the traditional, most of the landslide literature is actually not about retrogressive thaw slumps. It's about other kinds, the kinds that happen in California and places like that. And those are always main scarps down there. So that's the term I usually use. So these are dramatic features that have impacts on other resources. And so we thought, well, let's try to get a map of these. How many of them do we have? How much area do they cover? What kind of impacts are they going to have on these 5 national parks? So we've got a feature that is we got 82,000 square kilometers to try to do this on. And so what I developed what I describe as a semi-automated method for doing this. So here's we were fortunate about the time that I started my current position to get almost wall-to-wall coverage of our national parks in ICONOS 1 meter high-resolution satellite imagery. So that's like, okay, good, because these things are too, they have to get really big to see them on the Landsat image, and I wanted to be able to get all the small ones. And so it was great we got this ICONOS image, this ICONOS imagery. So that's what you see here is a ICONOS image of an area with a bunch of thaw slumps, and you can see them on there. And it's not that hard to scan across an ICONOS image and spot the retrogressive thaw slumps. I mean, sometimes there's some ambiguous features, but you can kind of click on each of these. The hard part is mapping them. And so the way I went about doing this then was to take the ICONOS image and compute NDVI, normalized difference vegetation index, which uses the infrared and red wavelength bands to compute an index that basically helps you separate unvegetated areas, which have low NDVI, from vegetated areas. So that's nice. You can see the thaw slumps here are nice and black, so that's a good start. And then we can threshold the NDVI image to get basically vegetated and unvegetated areas, and then we can convert that raster to polygons. And so now we have all the unvegetated areas basically, plus water, a few other dark objects, bare rock. It frequently has low NDVI unless it's white. And convert those to polygons, and then overlay dots that came from digitizing all of the retrogressive thaw slumps, and then run a GIS operation where we'll say keep all the polygons that have a point in them. And so there we go. There's our There's our map of retrogressive thaw slumps. Sort of painstaking, but it got the job done. And it was a good way to eliminate lots of sort of look-alike areas that also that are unvegetated, like gravel bars and gravel ridges and that sort of thing that also have a low NDVI and bare soil on them, that kind of thing. So that was how I did it. And as I said, we had wall-to-wall coverage of the parks. So here's the result: all the retrogressive thaw slumps in our network. Actually, I probably missed a few. I probably misidentified a few, but this is, this is close. So I found 724 retrogressive thaw slumps, and they expose, I was able to add up their areas, right? And they expose 2.4 kilometers squared of bare soil, which is, what is that, about a square mile, I guess, right? Something like that. So it's, so they are, let's say locally, there's a lot of them, right? I mean, look at all the yellow dots. So there's a lot of them, and they're locally important where they're spilling mud into some lake, but they aren't, in terms of percentage, remember we had, what did I say, 82,000 square kilometers of bare soil, so they aren't wholesale altering the vegetation of this landscape. They are still localized, of local importance, but there are lots of them. So anyway, that was an interesting result, I think. And they're mostly in No-Attack National Preserve, which is this one here, and Gates of the Arctic National Park and Preserve, right? So that's where most of them are. One thing that I was a little surprised about was that they weren't in Bering Land Bridge National Preserve, which is the northern half of the Seward Peninsula. And that's where all of our ice complex, also known as Yedema, extremely ice-rich, syngenetic permafrost, the ice lust complex stuff. That's where that is in the parks I work for. Most of it, anyway, is on the Seward Peninsula. And there's a lot of thermokarst, obviously, that occurs in those sediments. They're extremely ice rich. But what was interesting is that I didn't identify these as being retrogressive thaw slumps because, strictly speaking, a retrogressive thaw slump should move away from, so the thermokarst that occurs in Bering-Lanbridge on the Edema sediments, basically the slope ends in the water. It could be either the ocean or a lake, and they tend to not eat their way inland like a retrogressive thaw slump should. They pretty much stay right by the shore, and they don't go a long ways in. So those are not, strictly speaking, retrogressive thaw slumps. They're just thermokarst. That was a bit of a surprise because those we thought were our most ice-rich sediments, but they weren't. I guess not enough to make good retrogressive thaw slumps. And also, I think that the topography is flat, which also inhibits their growth there. So here's some some of the environmental characteristics of all the when we had all these thaw slumps mapped, so I was able to then compare them to various environmental factors. And Andrew Balser actually did more of this with his thesis, where he looked at the environmental features that are associated with these slumps. But in general, they're typical mesic upland tundra vegetation in my area. They also occur in the taiga and other parts of the world. They occur on all slope aspects. You might say, oh, they'll be on southern slopes because that's where it thaws. But actually, they're more common on northerly facing slopes in my study area, although they do occur on all aspects. And they are on moderate slopes above creeks and above lakes, but a lot of them are actually up on a slope somewhere and far enough that they're probably not shedding a lot of sediment into a lake. In other words, it seems that the water peters out somewhere before it gets to the stream. In all those situations, and in my study area anyway, in those parts that I work at, they are mostly in late Pleistocene glacial deposits. So they're not in Aeolian silt or something like that. They are mostly in glacial deposits. Both the Itkilik 1 and Itkilik 2 aged glacial deposits, which I'll talk more about that later, but Itkilik 2 is the last glacial maximum. Itkilik 1 is prior to that, more than 40,000 years ago. So we have both of those in the Brooks Range. And actually, the Itkilik 1s are more extensive because in a lot of places in the Arctic, the late Pleistocene glaciers were not the most extensive ones because presumably they were starved for moisture at that point. So we have more extensive glaciers actually prior to where the maximum occurred in the rest of the world. And a lot of our retrogressive slumps are actually in those older deposits. And our on-the-ground observations revealed that there was actually glacial ice preserved in a lot of these thaw slump escarpments. And that's what that picture shows. And I'll talk more about that later. But these slumps range in size from basically too small to map to up to 5 hectares or so in my study area. And this is basically our most dramatic thaw slump. This one on the Noatak River, and it's along. This is the Noatak River here, and you can see the plume of sediment coming down. And your first thought would be, oh, this must have been started because the Noatak River, eroded in and got it started. And that may have had a role in it. But I was interested to see that if you look at an old airflow that we have, 2008, you can see that actually these lines heading uphill from that thaw slump are actually active layer detachments, which is a thin, faster landslide, basically, that happens due to permafrost thaw. And we know that we had a big episode of active layer detachment activity in the summer of 2004. And judging from the amount of vegetation on these detachment scars, that's very likely what those are. So actually here, what might have happened is that permafrost was actually exposed by the active layer detachment, and that's what set it off. Actually, Andrew Balser, who did it, who in his journal Geophysical Research publication, he also did a thesis here at UAF. Most of you probably know him. Studied the initiation of thaw slumps in this same area in the Noatak Preserve, and using SAR data, and he found that most of the 21 that he studied actually began during the period of 2004 or 2005. So there was those warm summers back then that led to initiated many of these thaw slumps, and then a lot of them are still active from that initiation date. And he also found some that had been around before that too. So it isn't not every thaw slump began in 2004, but a lot of them did. And another thing, just some more trivia about thaw slumps. So these are this one. I have in the corner of many of these slides a code number for the slump, and that's for me to remember which one it is. Because you pull out slides and then you can't figure out what it was, and so those help me remind me which slump we're talking about. So this one, it has our highest escarpment, 20 meters, and it was about 4 hectares in 2016, and we have a few that are a little bigger than that, 5 or so, 5 hectares or so. This one is a little enigmatic in that, well, I was only there once on the ground. I've flown over it multiple times, and it was, of course, the escarpment was really treacherous, and I wasn't able to get close, and there wasn't obvious ground ice in the escarpment. I'm sure it had to be ground ice in there, otherwise you are going to get a thaw slump. But I did not ever figure out what drives this one, which is too bad because it is our biggest one. So several other slumps in my study area here are 5 hectares or so, a lot of smaller ones, and there's quite a few that have main scarps in the order of 5 to 10 meters. This is the only 20-meter high one that we have. And just for some trivia about thaw slumps and who's got the biggest thaw slump. Some of you have probably heard about the Selawik River thaw slump, and that's probably the biggest one. That's the biggest one I know about in Alaska. Area-wise, it's 5 hectares, so it's about as big as some of our biggest ones, but it's a little deeper. It's 25 meters deep. It's right in the Selawik River, and like that, Noatak slump is also shedding a lot of sediment in the river, and is of interest because of the effect on fisheries. However, if we go outside of Alaska, there are some really big thaw slumps, bigger than ours. So in the Peel Plateau region of Canada, they range up to 50 hectares in size, and one there that I saw reported in the literature was 25 meters deep. But then the world champ thaw slump actually is in Babagai, Russia, 80 hectares, 70-meter high escarpment. So that's the monster thaw slump there. So we've got a lot of them, but there are bigger ones elsewhere in the world. Now, of course, the question immediately comes up, all right, we've got all these thaw slumps. Is this something new? Does this represent climate change, having a big impact on the ecosystem or not? And so that was one of the reasons that we've launched this monitoring program. And, unfortunately, I don't have an unequivocal answer to that question, because it basically would involve orthorectifying and classifying the slumps on many old air photos, right? And I haven't gotten through that task yet, but I have done some local investigations. And my sense is that we have more thaw slumps probably now than we did in the era of the AHAP photography, which is around 1980, which is really good for mapping thaw slumps, by the way. It has good enough resolution, color infrared. Color scheme is great. So my sense is that we have a bit more now than we had back in 1980, but they certainly aren't a new phenomenon. They've been around. And you can really see that on this. So the upper photo here, 1977, is a color infrared AHAT photo, and all the things labeled 1 on here are thaw slumps that were active at that time. Or in the case of these two on the left here, the escarpment is looking a little rounded. So I'd say these have probably just died out, and this one over here on the far right actually looks like it grew a bit further after the photo was taken. But anyway, we had all those active slumps in the 70s, and what we know now, that it takes many years for a slump to get to the size of these. So that means that most of their growth actually took place in the 60s and 70s, probably, which was not a particularly warm. The 60s were not a warm time in Alaska, right? And so obviously we were able to make thaw slumps work even in the colder conditions of the 60s. And you can look here at labeled 4. There's an old scar of one that occurred who knows when prior to that, many decades, and it revegetated. So then in 2008, you can see the revegetated scars from the 1970s slumps sitting there, and then labeled 2 are a couple of new ones that have occurred in a place that was unaffected before, and then 3 is an interesting slump because it's a big one that is actually it's partially on new territory and partially actually overlapping a previous thaw slump. You can see where it overlaps one of the ones labeled 1 from the 70s. which is interesting because that indicates that, and there's a big escarpment, you know, at the front of that thing, and that indicates that the first time didn't get rid of all the ice, right? There was still enough for it to happen again. And these multi-generational slumps are really not that unusual. They happen. And so a typical escarpment exposure here, glacial till, you know, somewhere in the 1.5 to 2 meters thick, and then glacial ice underneath. And this is Pleistocene relic glacial ice. You know, in other words, 20,000 or more years old. It's been sitting under there. And then below that, of course, there's this slurry that results from taking nearly pure ice and mixing it with some mud above it, and that's what you get. And you know, for a while, this whole glacial ice hypothesis was a bit controversial, but I was pleased to see recently a paper came out from some workers in Canada who've worked a lot on these, and they have agreed that the places where you get a lot of thaw slumps is where you have relic glacial ice. And in northwestern Canada, they are actually within the limits of the Laurentide ice sheet, and there's still ice up there, and that has really, and they've kind of concluded that that is the really big driver of thaw slumps in that region. You can get thaw slumps in from other kinds of ice, but it seems like in landscapes where you have a lot of glacial ice preserved, then wow, you've got a real good setting to produce thaw slumps, and so they tend to be really common in those landscapes. And so yeah, here's another one, just an example, glacial till over glacial ice. And if you think about it, you know, in continuous permafrost, if you have glacial ice, you know, wasting away, and it's debris-rich ice, and eventually the stuff will end up on top, and as soon as you get, you know, 1.5 meters or 2 of material on top of the ice, you're in the continuous permafrost zone. There's really no good way to get rid of the rest of the ice because it'll be preserved in permafrost. So it's really not that surprising that we have preserved glacial ice in a few select places in the continuous permafrost zone. You know, another example of glacial ice under an exposure of glacial till in the Noatak Valley. Once in a while, you know, you don't always see the ice exposed. A lot of the times there's slump material that covers the face, and you don't really see the ice. Or sometimes you'll walk along the slump face and not see anything, and then here you see the glacial ice exposed, right? Just a little sliver of it that's not covered by slumped material. So you don't always see the glacial ice, and I'd say that probably I actually only have direct evidence of glacial ice in, you know, maybe a little over half of the slumps, but it's the most common kind of ice that you see exposed there, but not the only kind. So we also have big ice wedges exposed in some of our thaw slumps, and these are on the older glacial deposits. So these Achillic 1 glacial deposits, which are older than 40,000 years, you know, these were named and mapped by Tom Hamilton of the you know, formerly the USGS, and he you know, identified them as being since the last interglacial. In other words, younger than the last interglacial, but prior to radiocarbon dating age. So that makes them older than 40,000 years old. And so these are glacial deposits that sat around during the extremely cold conditions that followed their deposition during the last glacial maximum, when all the Yedema was forming on the Seward Peninsula and those kind of places. And we got these big, dirty ice wedges that we are familiar with from Yedema deposits in the glacial deposits. So these are not uncommon in thaw slumps that are on the Achillic 1 glacial deposits. Of course, a little circular. If we see these big ice wedges, then we presume that it was Achillic 1 because that's when they probably formed. If they're Achillic 2 glacial deposits, it's been basically warmer climate ever since, and we assume that these big dirty ice wedges probably didn't form there. So now what I'm going to do is I'm going to zoom you in a little closer. You know, this looks like glacial ice and glacial till. You can see the rocks in it, so that tips you off that it's not lost like we usually have. A lot of our ice wedges are in. I'm going to zoom you into that little spot there, and so you can see some rocks here. And I was a little suspicious about this stuff that was in the lower half of the picture. So you can see that little hollowed out spot. That's where I scraped out a little bit of the material. This is this is a quick gravimetric moisture content, the quick method. This is the quick field method. So this stuff looks like glacial till, and I put a little bit of it in my hand and then held it for a few seconds, and that's what it came to be. So actually what that stuff is, that was actually debris-rich glacial ice and not glacial till. So a lot of that gray, rocky-looking stuff that's down there is actually debris-rich glacial ice and not glacial till. And so you have this kind of funny situation where you have ice wedges growing in glacial ice, right, below a mantle of glacial till. So, this picture here is, this is my favorite ground ice exposure that I've ever been to. This is like a theme park if you're into glacial ice or ground ice, permafrost ground ice. So what I interpreted this exposure to be is the nice clean white stuff. That's the Holocene glacial ice. That's the that's the Holocene wedge ice formed in ice wedge polygons, where it's clean because the water flows in there through organic matter and gets nicely filtered, and you get this nice white ice. The Pleistocene ice wedges are much bigger and dirtier, and those come down and they penetrate through, in this case, a couple of meters of loess. So there was a little bit of loess capping this glacial moraine, but then they continue down into the glacial till and then into the glacial ice that's underneath the glacial till, and you can see a rock sitting there in this horizontally bedded glacial ice underneath. So very complicated but interesting ground ice on these older moraines, and really nice exposures in the main scarps of these thaw slumps. And just getting back to that notion that retrogressive thaw slumps can rework an older slump area. So here we have a big thaw slump. All these are in the Noatak Valley that I've shown you so far. And you can see the outline of an old slump that had been up here and got revegetated. And now this slump is working its way through both fresh material on the lower part and then the old thaw slump on the upper part. And there's some nice ice wedges exposed in the undisturbed part, but even in the old slump you can see reworked till with glacial ice, and then some of these wedges that are penetrating down into the glacial ice visible even in that area where the slump had gone through before. And it's interesting, of course we're not dragging drill rigs into the Noatak Preserve, so we don't know how thick this glacial ice is, but obviously you can sweep across this losing a meter or two of ice, or who knows how much we lose each time. I'm assuming that each time a thaw slump passes across here, we lose a couple, 3, maybe 4 meters of ice. But apparently there's many more down there waiting to be swept up the next time, the next generation of retrogressive thaw slumps. We don't really know how much is there. But I guess that's why glacial ice is so ideal, besides being, of course, very high in water content so that you can flow this stuff away. It also is very thick, and it doesn't decline in its percentage ice as you go down like wedges normally do, right? I mean, syngenetic wedges can not decline very much, but at some point you run out of water as you go down if you're talking about that kind of ice. But glacial ice, it should go till it runs out at the bottom of what was originally the glacier. Okay, so now in addition to just mapping all of these things, we decided to try to monitor a few of them intensively, and to try to get a feel for, how fast do they grow, what volume of material, and that kind of thing. So we selected a few of these slumps that we had identified as being like on major water bodies, or clustered together so they were fairly easy to get to, the big dramatic ones. So here we are back at this one in the Noatak River, and we shot overlapping aerial photographs that we could use then to create 3D models using structure from motion software. And we have overlapping aerial photos that were shot. I shot a bunch of them in the 2010 to 2012 era, and it was pretty easy to do. You can be up there for almost anything, and if you have a good camera and you don't mess with the zoom, you can shoot a bunch of overlapping photos and get your 3D model. In those days, what I did was I actually got a helicopter a couple of times to go out and put a total station up and measure, set out some targets and get the dimensions of these things. So that's the way we did it back then. What I've done since then now is, since 2013, Matt Nolan has gone out and flown some of these for us. And some of you are familiar with his technology where he gets very exact camera locations from GPS in the airplane, and that allows us then to create a 3D model that is actually georeferenced and scaled properly right from the start. And so what I'm doing now, I'm in the process now of analyzing all of this. So this is a work in progress, and I haven't gotten as far along as I'd hoped to. I'm in the process of going back over all of my old photos and registering them to the newer ones and computing changes in the size and volume of these slumps. And we have about 20. We're probably not going to maintain that many into the future. But so then, Structure for Motion software, we can create a 3D model from the overlapping photos, and then drape the original photos back over that model to make an ortho. And then these ortho photos and the DEMs, the models, are really useful for all kinds of measurements. So what I'm going to do is just show you some examples of the growth of some of these thaw slumps. And the examples I'm going to give you are mostly from this, are all from this area right here with the green circle. And then I'm going to be showing you a little bit of weather data, and that comes from the NOAATech RAWS weather station, which is pretty close by. So NOAAT 148, a pretty typical thaw slump. You can see the landscapes of the upper NOAATech Valley. This is what it looks like. It's this rolling glacial terrain with these kind of rounded mountains, and there's the slump right there. You can see the escarpment on the left side in the shadow. And this is one of the Ikillik 1 aged glacial deposits. So here you can see my coworker standing on this bit of turf here that's partway up, so you can see that he would be this high if we moved him in here to give you a scale for this. So this is about a 5-meter high escarpment, and basically, you get to these escarpments to look at the ice by hopping between these turf boats, because usually you'll sink if you get in the mud there on the way. So these shiny areas here are then the Pleistocene ice wedges. I think we did see some glacial ice at the very bottom in one spot of this one, but not very much. So we first knew about this because we had this 2008 ICONOS image. That's how I found this thing, and so that's the image you're looking at here is the first one, the first glimpse we have of this slump. And then we went there in 2010 and shot overlapping photos to get a 3D model in an ortho, and then managed to get there in 11 and shoot photos again, and in 12 shot them again, and then Matt Nolan actually flew some for us in 13, and he was up there again in 14, and then also 16. So we have a real time series of this particular thaw slump, and you can see then, it's easy to map then the progress of the main scarp through time from at least 2008 through 2016. And one thing I'd like to point out is that notice how in the last year you started to see these elongate turf blocks along the slump face, and that has to do with the change in the behavior of the slump growth, I would say. So for the first 4 years of our monitoring, we had a main scarp retreat rate of about 12 meters a year from 2008 to 2012. But then in the last couple of years, 2013, or last 3 years, 2013 to 2016, we slowed down to about 5 meters a year. And I think that was associated with a change in the morphology of the scarp. So the classic retrogressive thaw slump has this vertical face of some height, a couple meters to 70, I guess, above the guy, and the material basically thaws in the front, and then overhanging junk falls in and it flows down. Now, a lot of slumps actually have a sort of a partially vegetated scarp, and it's more indistinct, where you actually don't even really expose the permafrost. What you end up doing is tearing apart the turf into these elongate blocks, and you're getting melt because the active layer is basically thicker than the amount of overburden here, so you're getting melt, but without actually exposing a face. And that usually seems to happen, those can actually move pretty quickly, but they are, I'd say, a sign usually that you're slowing down, that this particular thaw slump growth rate is slowing down. And then with these DEMs, we're able then to compute the elevation change between visits. So here in dark red is subsidence of about 5 meters, corresponding with a 5-meter high main scarp. And then out in front of that area, you can see in dark blue here, it's plus half a meter to plus 1.7 meters is the legend there. What happens is that material oozes down, and it basically piles up just below the active area, and you end up accumulating a bit of material there. So that's a very common mode of growth of these things, is that the scarp retreats and you have big subsidence near the scarp, but then you actually get a little bit of rise of topography a little bit further down. So that's kind of the typical growth scheme of the slumps. And what I've done here now is I've plotted the area of the scarp, or excuse me, of the slump, 0 to 2.5 hectares, versus the thaw degree days cumulative from the first visit in 2008. So I computed thaw degree days from that NOAA RAWS weather station. And the reason that's helpful is if you think about it, if you one year you visit in September, next year in June, you might miss a year. The yearly growth of these things is not really probably as good of a measure as plotting it against something that standardizes the time between your visits. And so I thought thaw degree days might do a pretty good job of that. So here we have 2008 to 2016 plotted in area versus thaw degree days. And as you can see, it was moving kind of a linear growth in area, and then it started to die down a little bit towards 2016, and it seems to be settling down, and I'm expecting it to stabilize. Now that is, of course, tempting when you see this straight line to say, well, let's just extrapolate that back to 0 and find out when the thing started. And it's easy to do in Excel. Whether it's right or not is, of course, another question. But in this case, if that linear growth rate had been going on since day 1, we can extrapolate back that it was 6,000 some thaw degree days, take us back to the basically the x-intercept of the axis, and that number of degree days occurred. So we basically count back 6,936 degree days back from our visit in 2008 using the climate data, and arrive at a time 0, which comes out to be 2003 July 21st. Actually, we have some direct evidence about when this thaw started, or when this thaw slump began, because Andrew Balser actually searched old SAR images for the dates when these thaw slumps were first visible, and he actually did that for a bunch of the ones that we've been monitoring. And the first year SAR image that he saw this slump was 2004. So I actually my guess would be that it actually began in 2004, and that my extrapolation is a little bit off. But anyway, at least we know that we're in the ballpark, and it's probably associated with that extra warm, wet summer that we had in 2004. It was wet up there. It was dry here, right? That was the big fire summer. But there was some rain events in the spring that probably were that, along with the really warm and early spring, probably were what drove the active layer detachments and the initiation of these thaw slumps. So here's just another example. These are a couple of big ones that also in the upper Noatak Valley. These facing directly north, by the way, so obviously that didn't keep them from being, actually, this one on the left had the fastest retreat rate of any that we have been monitoring, and it faces directly north, so go figure. That obviously doesn't matter. So the main scarp retreat rate on this one, from 2008 to 2016, has been 32 meters a year. And that's the fastest. And well, this one is the one on the right here next to it has been almost as fast. So that's kind of the limit that we've seen. And of course, 10 to 20 meters is more typical, and the ones that have stabilized are even less. And that's just this is what the main scarp to that thaw slump looks like. So it's pretty typical, a couple of meters of glacial till over glacial ice. Those are the ones that really move fast because it turns out that these ones that have the glacial ice underneath them are the ones that really move quickly. Ones that have less ice don't seem to be moving as fast. But I haven't worked out, that whole business of the growth rate, and most of that's in the future when I get more of this data analyzed. So in this case, we seem to have kind of a linear growth rate through time. I plotted then again the area of slump NOAD 069, which was the one on the left, the area of that slump versus thaw degree days, and that one doesn't seem to be slowing down yet. At some point, it'll encounter less ice-rich material, get to the top of the hill. I'm not sure what will stop it, but at some point we expect it to slow down, and I hope to get a better idea of what causes that. But at the moment, we can say that this one doesn't seem to be slowing down yet. And if you extrapolate it back to zero, count how many degree days it takes to get back to zero area. That's negative 3733, which puts you at 27 August 2005, and in fact, that's when Andrew Balser first spotted it on a SAR image. So we have a pretty good, I think, reason to believe that thaw slump also began in that 2004-2005 era. I don't want to give the impression that all of our thaw slumps began then. We have some that obviously are older than that and have been around longer. And the one I was working at just before I came here, I almost made a slide of it because I was working up the data, and it obviously started quite a while before that. And he also noticed that too. Some of the slumps he was able to identify on the SAR imagery back in the 90s or even the 80s. So this is back to that big no-attack slump, just again illustrating the growth through time, with the red being subsidence. In this case, the dark red is subsidence of more than 16 meters, so that's really a lot of subsidence. And then the blue is accumulation, which tends to occur just downslope of where the subsidence is occurring. And in this case, I did a quick computation of the volume that was lost, of material lost between 2008 and 2016. Turns out, we had a loss of 168,000 cubic meters of material, and deposition or gain of the surface, rising of the surface below of 25,000, I guess, for a net loss of 143,000 cubic meters, and which doesn't mean a whole lot to me, but I converted that to the depth of a layer on a football field. So if you take an American football field and cover it with 27 meters of material, which is 89 feet, that is the amount of material that was lost out of this slump when it grew from 2008 to 2016. Now, of course, the next question is how much of that was solid and how much of that was water, and we don't know. We don't have ice contents. I'm going to guess that more than half of it was water, but it all ended up in the Noatak River. Lots of old, ancient water, and a certain amount of sediment too. So for the future, our monitoring program at the Park Service is long-term. The idea is that we've picked things that we feel that we can keep doing over the long term, and so we have another iteration of mapping these slumps and other permafrost thermal erosion features coming up. I did the first one on 2006 to 2009. Iconos imagery, and the idea was to do it about every 10 years. And I'm probably not going to try to do the whole network again. I'll probably just, now that we know where they occur, and unless we get evidence that suggests that they're occurring somewhere new, we'll probably narrow it down a little and pick some of the areas where they're really dense before, but that's coming up in the next year or two. And hopefully again after that, and we'll see if they are more or less than they were in 10 years ago. And then we're also planning to continue monitoring of selected thaw slumps by 3D modeling. We'll probably scale back a little. We've at one time or another have taken pictures of over 20 of these, and that's a little much probably to maintain in the long term. So we'll emphasize maybe 5 or 10 of the most active high-impact ones, the ones that people are asking about, that are dumping sediment into salmon spawning rivers, for example, like this one, and we'll try to keep track of those. And the idea is that we will try to get new photos to make models of those every 2 or 3 years if possible, depending on availability of funding. Although it can be fairly cheap if somebody's flying up there and you're willing to work with the oblique aerial photos. You have to go up once in a while and get some georeferenced ones, but you can use these ones that are shot out the window of an airplane if you're willing to do some certain amount of manual georeferencing of landmarks to the ones that you have georeferenced. So it can be fairly inexpensive if you've got people going up there doing flights anyway. So anyway, that's the future of the fossil lump monitoring program for Arctic Inventory Monitoring Network. And so that's all I have. And if there's any questions, I'd be glad to answer them. This is me standing in front of a main scarp exposure.
Thank you, Dave. Really cool. So we'll take one question here, and then we'll move and see if there's people online that might have some questions, and then I come back to you guys. So and if you're online, you can write your question either as you can write it down on the commenting board, or you can speak up and make sure you have your microphone on, because we should be able to hear you.
So, Roger.
Are all these initiated by some sort of active layer detachment?
No, I don't think so. But that it is a problem though, because you don't know about them until they've grown a while, right? So it's kind of like well, you can maybe relate to, you don't really know what the pre-fire vegetation was on those fires because you didn't manage to go do it before the fire, right? It's the same kind of thing here. I think some of them form for other reasons. Some of them can be started by fires, for example, or a little riverbank erosion. I think maybe just a little kind of random thermokarst. Anything that exposes it a little bit can set it off if you've got the right ice there. So I think that quite a few of them probably began in Arctic Network as active layer detachments. But actually, come to think of it, there's really only a few that where there's really a smoking gun, where you have the retrogressive fossil lump and then the active layer detachment like going up from it. I've really only seen that a couple of times, so I'd have to say that probably it's usually something else.
Yeah, I was just curious about lightning strikes and really small fires that could initiate something like this.
Yeah.
And once they start going, you have an intuitive feel how they could continue, but how they're initiated is a little more problematic.
Yeah, and particularly since your first thought is, oh, there was a cut bank on the river or something, right? But actually, not that many of them begin at the cut bank of a river. A lot of them are up on the slope somewhere. And so I think another thing that could happen is you could have you could have some kind of a water track or something on the slope, and you get beaded streams and a little bit of thermokarst, maybe a little bit of ice wedge degradation up on a slope. Any of those things I think could set it off. A fire. I think in forested areas, I think in Canada that have been demonstrated to have started with fires. So we certainly get active layer detachments after fires too.
All right. See if you have some questions from people online.
Yes.
So speak up and give them a couple seconds to unmute themselves.
Yeah. Right.
All right.
Got a comment.
Yeah.
I was always struck when you first showed me these pictures by the juxtaposition of the different types of ice and how complicated, and it just kind of threw out everything that I had, envisioned. But, the permafrost tunnel, for example, has some of that. You can see ice wedges and things, but and I'm not really sure what the larger implications are of the fact that you have all these, like you say, they're buried deep enough. And this isn't just related to retrogressive thaw slumps, but I guess it's just hard for me to figure out, does it matter that we have all these different types of ice down there? Certainly if you started imagining this area becoming a discontinuous permafrost area, maybe 100 years from now or something like that, then it would have a really big impact on how the hydrology changes, because you've got these different massive conflict juxtaposed. I mean, what were your impressions when you first got in there and started seeing different types of ice?
Well, one thing I noticed was that the really fast-moving ones are actually the ones that have just a thin layer of till over glacial ice. Those are the ones that are really fast. But the high ones, the really high ones, usually are the ones with the wedges too. And so volume-wise, those are probably important too. But they don't seem to go as fast. And one thing I'm hoping, now that I have all this rate information, I'm hoping to maybe be able to sort out that. Although, unfortunately, I've only been on the ground at most of these briefly once, basically, because that requires a helicopter. And usually most of this is flyby kind of stuff. So, but as far as the bigger implications of all this glacial ice is, basically, I think what we are looking at is, a lot of that is, we're not above freezing yet up there, right? This is a discontinuous permafrost zone. But I think, if Santosh's predictions come true from the modeling that the Geophysical Institute has done for us, and we start seeing major permafrost degradation in that area, I think we're going to reenact what happened in the upper Midwest after the Pleistocene glacial. We're going to start disintegrating all this ice and watching new kettle moraine terrain forming in northwestern Canada and in certain parts of the Brooks Range. At some point, if permafrost over glacial ice becomes unstable, then it's all going to go eventually, and there should be a lot of these. At the moment, I'm pleased to say that so far, it's not. We don't have fire and brimstone happening there yet, but predictions happen as we think they could.
That relationship you showed me with aspect, I think you showed there was more of the frost lumps on northwest slopes. Mm-hmm. Do you think that's because of snow persistence or something like that, or do you have an explanation?
Don't really have an explanation, and I don't recall if Andrew looked at the same thing. I don't have a good explanation. I wonder if maybe it's possible that north-south slopes have had the ice exhausted prior, and then there could be things having to do with snow. That could certainly, these escarpments tend to accumulate snow if they're in the right aspect, right? Which, keeps them from freezing, but also protects them in the summer. So I don't really know the full effect. So yeah, that aspect thing, I have to admit, I don't have that sorted out. But other than to say that we do get them on all aspects, so any rule that you come up with is going to have a lot of exceptions.
Yeah, I was curious what sort of slope values you're seeing where these are occurring, or would you say it's more driven by the presence of that glacial ice?
Well, I think slope is important, because you've got to get the material away from the wall, right? And it won't happen. Well, actually, on glacial ice, you need hardly any slope to accomplish that because there's so much water. But both Andrew and I ran statistics of the slumps versus slope, and actually I had it on a slide and I took it out because I haven't redone it since the good DEM came out. I ran it a few years ago back when all we had was that med DEM with 60-meter DEM, and I really didn't trust the results so much. But I think though, percent-wise slopes of 6 to probably 25% slopes, if I remember right, are about what they're on. So gentle enough so that you're not looking at cliffy stuff that doesn't have ground ice in it, rocky substrate, but then enough slope to keep moving the material away from the scarp so that it can continue to go. I think, I'm assuming that these, the ones that form without glacial ice probably have, for whatever reason, a variety of massive ice bodies in there. It could be wedges or other kinds of ground ice, and then enough slope to keep the stuff moving away so it can continue to grow and not stabilize.
I wonder what the key concern is for the Park Service for transport into the river systems. So you mentioned spawning habitat. So is it mostly particulates that are the main concern, or is it like organics or trace metals?
Yeah, there's been a little work done on that, not by us, but by actually some people cooperating with UAF and some other schools outside, where I think they found particulates, and there's nutrients too, And I haven't heard any mention of trace metals or contaminants. I think the main resource concern caused by retrogressive frost slump that I'm aware of is the cellular slump sits right above an important sheepfish spawning zone. And so that deposition is probably causing some trouble for the sheepfish. And I don't remember how much, that's something that Ray Hander has worked on, who works for Fish and Wildlife. But I'd say that that's probably the biggest concern, is because, salmon too like these clean gravels and they have to spawn on, and if you get a lot of new silt, that could certainly change things. In the lakes, there's some lakes that it's kind of hard to say what the impacts are. There's some lakes, there's one lake up next to Gates of the Arctic, it's called White Lake, and it's called White Lake because it's ringed by frost slumps, and it's always been white. And so it's like, well, that's the way White Lake is, in the future there could be more White Lakes, though, I'm assuming. And at one time I got a question about whether I thought all of these slumps were causing sedimentation that might be one of the reasons that you can't get barges to Noatak Village anymore. And my answer to that was I didn't think it probably mattered, because we're many miles upstream from there, and we're talking about that one football field of sediment, and Noatak Village is in a braided part of the river, which is going to be trouble no matter what. So I would say that isn't one of the concerns, and the fish thing is probably the main one. But of course, if we have, we don't really know how much glacial ice is up there. So in the year 2100, when a lot of it starts to disintegrate, then there could be more concerns. But they're probably mostly related to water quality. Although, I don't know, so many things will be happening under that scenario that this was just one of many. You start having these things could get a lot more widespread, and then you get a big change in vegetation and all that kind of thing. At the moment, that doesn't look like it's a big concern, but certainly it could be if they start forming everywhere that we have glacial ice underground.
Yeah, have you looked at the depth of thaw beneath that deposition area at all? So maybe if metallic is forming and you get continued subsidence or something like that?
I think there's probably some continued subsidence, but we haven't done the monitoring, and we haven't been back at the end of the growing season to do the probing. But that's something on the to-do list. It would be really interesting to know. I think in that country, I'd have to maybe look at the models. They're revegetating, and I'm assuming that they're getting a couple of meters of sediment, and that might be enough to protect it. If there is continued subsidence, you don't see. It's interesting below. When you get below that, saying about how you get the slurry, and then you get this kind of this little bit of a ridge of material that accumulates below that. When you go downhill from there, you don't see a lot of what looks like evidence of thermokarst. You don't see like pits and that kind of thing. It's vegetating over, and it looks pretty stable. But I certainly wouldn't swear that it is, because you know that there's just barely enough material to keep it stable. But that was true before. The thing is that there was turf. There was a good moss mat on top. Like you can see in those escarpments, there's 1.5 to 2 meters typically of till. And I think the active layer under the tundra vegetation is probably half that now. But without that tundra vegetation, it probably thawed the full 2 meters. And so you can imagine the scenario where that originally stabilized. But right, if we had time to get back to these places, which I don't envision anytime soon, we should go and do some probing.
During your time of observation, did you also find some frost slumps which stabilized during that time?
Yeah, some of the, there's some that when we went back the second time, they took the pictures again, they looked like they hadn't moved at all. The problem with proving that they completely stabilized is that the accuracy of our elevation surveys are probably plus or minus 20 to 40 centimeters, I would guess. So if you are getting some continued subsidence, it would be very difficult to detect. But we certainly have seen some that have slowed down and the scarp isn't moving anymore, and there's probably a little subsidence, although we have trouble detecting it by our methods. And I think that actually quite a few of them have done that. So, and it's hard to say. I think that might be partly a result of the fact that we didn't find these until they were in their prime, and some of them probably running out of ice to melt. And so we actually ended up picking a few that were near the end of their rope, and ended up seeing them end. But my general sense is that this will be something that'll be interesting when we redo our mapping. Is did we have a big episode in 2004 that's played out, and now we'll have a period of quiescence? Is that it's possible? Because a lot of them that we originally started monitoring have pretty much quit. And the ones I showed you were the interesting ones that are still going.
Sounds like Alaska gold rush, oil rush,
Right.
Tulsa rush.
Yeah.
Well, thank you, Dave. I'm sure if you would have some more questions for us, you're going to answer them.
Sure.
So thank you.